All right, so welcome to lecture 4. Where, previously we talked about Shannon's two important theorems, data compression and the channel coding / capacity theorem. And that was just to give you some sense of what Shannon did. And, the objective of the course from now on is to get to the point where we could look at questions like those that Shannon considered, but now we're going to try to model the channel as a quantum communication channel. And not only could we try to send classical data over that channel, but we could try to send quantum data. So to get to that point where we can discuss such topics, we need to go through a fair amount of background. And the book was Sumit. There's chapter 2, which is about mathematical preliminaries. That's what we're going to be doing now. And then after that, we have to talk about basics of quantum mechanics for quantum information. All right, so, some of you probably are already familiar with a lot of what we're going to talk about today, but nevertheless, we'll go through it. And indeed, if you have questions, I encourage you just to stop me and ask. Okay, so we're going to start with finite-dimensional Hilbert spaces. These are also known as complex Euclidean spaces. So for the finite-dimensional case, they're really basic and less technical. Okay. Throughout the course, we're going to use the Dirac notation, and that is this, vertical bar and angle bracket to denote a what's called a ket, and then that's just like a way of denoting a vector in a Hilbert space. So Hilbert spaces were always denoted by this calligraphic H. Okay, so let's start with a inner product. Oops, I want to do this. Continuous scroll. Okay. So what is an inner product? It's a function of two vectors in the Hilbert space, and it takes you to a complex number. Okay. And it should satisfy three properties, one of which is non-negativity. So if we take the inner product of the vector with itself, it's non-negative. And then this related property is, I think, often called positive definiteness, that it's equal to 0 if and only if the vector is 0. Okay. So when we get to quantum mechanics, quantum states, or what we call state vectors, will be vectors such that the inner product with themselves is equal to 1. Okay. Then there's this property of conjugate bilinearity. And apologies, it looks like the scan cut off the bottom of the page, but we have complex numbers, alpha 1, alpha 2, beta 1, beta 2, and vectors psi 1, psi 2, phi 1, phi 2. And they should satisfy this property. So like, if you take a superposition, a linear combination of the vectors psi 2 and phi 2, according to the weights alpha 2 and beta 2, and you do the same for psi 1 and phi 1, then the inner product satisfies this property. So it's kind of like the scalars come out, you evaluate all of the possible inner products, and then for the scalars that are over here, they get a complex conjugate. Okay. And then there's something called conjugate symmetry, which is that if you take the inner product in one order, doing it in the opposite order gets you a complex conjugate. Okay. So yeah, that's pretty basic. And inner product is something we'll be using a lot in the course. What are some basic vectors that we'll be using throughout the course? It's these ones. This is often called the standard basis or the computational basis. And we count from 0 because we're thinking in terms of computing, like in computing or computer science, you often start counting from 0. So the first vector has a 1 in the first place and zeros elsewhere, and that's the 0 vector, and the 1 vector has the 1 in the second place, etc. And then for a d-dimensional space, the vectors will be indexed by 0 through d minus 1. Okay, so that's the standard basis. And then if you evaluate their inner product, it'll come out to the Kronecker delta function. Okay, and in general, if you have vectors, so the standard basis is an orthonormal basis, and any other vector we can expand in terms of this standard basis with complex coefficients alpha I, and phi will have coefficients beta I. And we can define the inner product for this case, and the case that we'll have throughout the course to be this way. So like whatever's here on the right, you don't take the complex conjugate. For whatever's on the vectors on the left, you take the complex conjugate, and this is the inner product. And this inner product will satisfy all these axioms that we talked about previously. Okay, Euclidean norm, standard thing, take the inner product of the vector with itself and take the square root. And then you get a norm. There are various properties of a norm. I guess we haven't, that'll come later. I think it's listed in a later section of the book of chapter 2. Okay. There's a very famous inequality called Cauchy-Schwarz, and that's if you square the inner product, then it's less than the product of the square of the Euclidean norms. Okay. And Cauchy-Schwarz is such a common inequality. Like often when you're trying to prove some results or inequality, one of the first things you should try is the Cauchy-Schwarz inequality. Okay. The inequality is saturated if and only if the vectors are linearly, if they're related to each other by a scalar. Okay. If we, this notation indicates that this right here is the dual vector of psi. It's often called bra in Dirac's bracket notation. And a simple way to think of it as a row vector. So you just take all the elements of psi as a column vector, and then you take the entries and complex conjugate them. And this I right here is a row vector. Okay. More formally, you can think of it as a linear functional from a Hilbert space to a complex number. So like the functional would accept an arbitrary vector in the Hilbert space as input, and then when you evaluate it, it evaluates the inner product between psi and phi. Okay, so that's all I'll say about that. Okay, up next is the tensor product. And when does this come into play? Often we want to speak of qubits or qudits of d-dimensional systems. And information processing and computation is only interesting if there are multiple qubits. And so we need a way to mathematically describe that. If I have two real numbers, I would use the Cartesian product. But in quantum mechanics, we need something beyond that, and that is the tensor product. Okay. And so we use this notation for it. So you take a vector from a Hilbert space labeled by A and a vector from a Hilbert space labeled by B, and then this is the tensor product. Okay, so how is it defined? We'll start with a simple example. Suppose that these are standard basis elements like we defined previously. And suppose that HA is a two-dimensional Hilbert space and HB is a three-dimensional one. Then we could take 0, tensor 2, And then the 0 vector would have a 1 in the first slot, and the 2 vector would have a 1 in the last slot. To evaluate the tensor product, you take what's on the right and you place it kind of on top of what's on the left, right? So I take this and then I place it next to the 1. I take this, I place it next to the 0, and then multiply entry-wise 1 times all the entries, 0 times all the entries. Then I get this vector. And so that's a way that you can have a vector representation of the tensor product in the standard basis. Okay. That can be helpful to do this for understanding the tensor product, but what we want to do, what you'll find yourself doing eventually is you won't be doing this. It's easier to work with the tensor product directly and just know its properties. Okay. And we'll be thinking of how matrices act on tensor products of vectors. And then it's easier just to know the properties of the tensor product and work with those properties rather than like writing out these steps explicitly every time. Okay, more generally, this is a way you can define the tensor product of two arbitrary vectors. So we can, like we did previously, we can expand psi in terms of alpha I coefficients and phi in terms of beta j coefficients. And the tensor product will just be, you know, these coefficients will multiply each other for each index, and then there'll be a linear combination of these, the tensor product of the standard basis. So when you work that out with respect to the standard basis, for a similar example with 2 dimensions for A and 3 dimensions for B, again, you'll do this kind of stack and multiply, where you take what's on the right and you stack it on top of what's on the left, and then you multiply. Okay. A tensor product Hilbert space, I don't know if we've defined that yet. We defined the tensor product of vectors. The tensor product Hilbert space is going to be the span. You pick an orthonormal basis for A, another orthonormal basis for B. You evaluate the tensor products of those, and then the linear span of all of those vectors. So all possible linear combinations of these is the Hilbert space, is the tensor product Hilbert space. Okay. There's something else called direct sum, and this is a different kind of operation between Hilbert spaces and vectors. This is where you merely stack. You don't multiply, also you just stack. So the direct sum of psi and phi is the vector you get by, first, it's a column vector where you just list all the entries of psi first, and then you list all the entries of phi. Okay. Any questions so far? Maybe this is basic stuff. Okay, good. Linear operators. So these are functions from one Hilbert space to another Hilbert space. And we're going to be using linear operators all throughout the course. You know, like linear algebra is like, should become secondhand, you know, nature to you. So a linear operator is a function that satisfies this property of linearity. You know, x multiplying a linear combination of vectors is equal to the linear combination of x acting on each individual vector. Okay. And sometimes as a shorthand to indicate, oh, it's an operator going from Hilbert space A to Hilbert space B, we'll use this notation, A to B. Okay. That can come in handy to keep track of things. We define linear operators in kind of an abstract way. There's a more concrete way to do so, and you can identify operators with matrices, two-dimensional matrices, through a matrix representation. Okay, so for a matrix representation, what we can do is pre-multiply x by the identity operator and post-multiply by the identity operator as well. So we can use the identity operator is equal to the summation of the projections onto an orthonormal basis. Okay, that's like a standard result from linear algebra that I won't prove. And the same is true for this identity on the B system. And the A and B spaces could have different dimensions. In the book, we write all the indices and the dimensions, but I'm not doing that in these notes just because it's easier not to write it. So how do you get a matrix representation? Well, you pre and post multiply by these identities and then exchange the sums. And then this right here, this is a scalar, this is a number, okay? And these are the entries of a matrix. So we're defining these entries like this. And then this you could list in these entries you could list in a two-dimensional matrix, okay? So, and then these entries are called the matrix representation of X in the standard basis. We could take a different basis besides the standard basis, and these entries would look different in that basis. If we took a different basis, like maybe you take a Fourier transform of the standard basis, you get a different matrix representation. The point here is that even though the matrix representations might be different, the operators are the same, because you know, once you would actually use the particular vectors that you expanded the identity with respect to, then the operators would be the same. Okay, there's some notation that we're going to use throughout. Set of all linear operators from Hilbert space A to Hilbert space B. If the input and output spaces are the same, then we can just abbreviate one argument to this L. Okay, back to the tensor product, since this is going to be a key tool for us. How does a tensor product of linear operators act on a tensor product of vectors? Well, it does so like this. Okay, so you know, the first factor here corresponds to the first factor here, and the same for this factor and this factor. So the X will act on psi, the Y will act on phi. When we get to quantum information, we'll start saying things like, you know, the state vector of Alice and Bob is described by this tensor product state vector. And, you know, if Alice does a local operation described by X and Bob does a local operation described by Y, this is the resulting state vector. So we'll start saying things like that. And then that's how this comes into play in the physical picture. If we want, similar to how we did the tensor product of vectors in the standard basis, we can do so for linear operators as well. So the matrix representation of the tensor product is what's called the Kronecker product of the individual matrix representations. And it's, again, you do this stack and multiply. So I take everything here and I place it on top, you know, next to this entry x00, and then I do it again here, I do it again here, and do it again here. And so that's what's depicted right here. Okay. And then I didn't show all the steps. I didn't show all the details. It's there in the book. But what you then do is you do entry-wise multiplication of x00 times every entry of this matrix. Okay. And then there are certain properties of the tensor product that hold. Like, it's called a product because it obeys some usual properties of a product. Okay. So let's talk about what is the image of an operator. That is so if I have an arbitrary vector in the input space and I act on that vector with the x operator, I'll get an output vector phi. And the image is the set of all vectors that are reachable at the output by allowing for an arbitrary input to x. Okay. It's not the case that all output vectors in the output Hilbert space are reachable, especially if they have different dimensions. Okay. So that's what, this notion of image is useful. What is the rank of a matrix? It's the dimension of the image of that matrix. Okay. Later on, we'll talk about the singular value decomposition, which, presumably you've studied linear algebra. The fundamental theorem of linear algebra is this singular value decomposition. And what you find from that is that the rank of a matrix is equal to the number of singular values. Okay. The kernel of a matrix, also called null space, is the set of all input vectors that lead to the output being the zero vector. Okay. So, yeah, in some sense, it's like the vectors that lead you to nowhere, the vectors that lead you to the zero vector, if the zero vector is nowhere. Okay. The dimension of the input space of this operator is always equal to the rank of the matrix plus the dimension of the kernel, right? So it's like the dimension of the image plus the dimension of the kernel. Okay. There's something called support of an operator, and it's the set of all vectors that are orthogonal to the kernel. Okay. So formally, you define it like this. A vector size in the support of x, if it's in the input Hilbert space, and if it's orthogonal to phi, where phi is a member of the kernel of x. Here's a helpful picture that Sumit added to the book pretty recently that I think is nice, that kind of captures all these concepts in a nice pictorial way. So there's the whole input Hilbert space, okay? And the kernel is a subspace of the whole input Hilbert space. It's all the vectors that map to the zero vector, right? That's how we defined it. The support is orthogonal to it. The only place where they overlap is where the input is the all zero vector. Okay, the all zero vector will be in the image of an operator x, and it's a member of both the kernel and the support. Okay, but everything else is orthogonal, and so if they're orthogonal, it's like you can think of them as distinct spaces that don't overlap. And everything in the support maps to the image, that maps to something besides the all zero vector. Okay. So any questions about that? All right, seems like we're good. Okay, moving along. So the trace of a matrix, this is an operation that we'll do quite a bit. We'll get to interpretations of what the trace is later, but I'll say a few things now. A quantum state will be an operator that is a trace equal to 1. When we want to calculate probabilities of measurement outcomes occurring, we will make use of the trace. The trace can also have an interpretation as discarding a system, like throwing it away. Okay, so these are different interpretations that come up. Mathematically, it's defined like this. You take an orthonormal basis, and then you sandwich the operator of interest by that orthonormal basis. So to do this, the matrix should be the operator should be like a square operator where the dimension of the input and the output is the same. And so you just do this calculation and you get the trace. If you have a matrix representation, it will be the sum of the diagonal elements of the matrix. Okay. A commonly used property of trace is cyclicity of trace. So I think this is best illustrated with 3 operators. And what it says is that the value of the trace does not change under cyclic shifts of the operators for which you're taking the trace of the product of these 3, right? So I can do a shift of z over here. I get this, the trace stays the same. I can then shift y over here and get this, and the trace stays the same. And if you wanted to prove this, presumably this is one of the exercises in the book. I don't really know. But the way you would prove it is you can insert identity operators, right? I can insert identity operators here and then use the completeness relation that we talked about earlier. We'll go back to it. We used it here, right? The identity can be written as the sum of these orthogonal projections. So you can use that, and you can play around with the order to a certain extent, right? Like if I insert an identity here and I insert an identity here, we'll get the matrix elements of X, and then you have scalars and you can commute them with each other. And so to a certain extent, you can do that and then go back to this definition and recover this identity. Okay. Another operation we'll make use of is the transpose. So that's like a very basic thing that you learn in linear algebra. And for me, it was kind of surprising at first to learn that this operation plays such a fundamental role in quantum information. We'll find that it's used for understanding entanglement of quantum states. And it's also used in understanding things like how much quantum data you can send over a quantum channel. So it's really like, it's interesting that it plays such a fundamental role. The transpose is a basis dependent operation. So what do I mean by this? Suppose we have a matrix representation of X. What is the transpose? I should have written more here, but this right here is a matrix representation of X. So to get the transpose, you can do one of 2 things. You can flip these indices or you can flip these, and the operator will be the same by an index relabeling. Okay. That operation has been done with respect to this basis. If you expand X with respect to a different basis, the transpose will generally be different. It'll lead to a different operator. Okay. So, but a lot of the actual properties of the transpose that we use for like detecting entanglement, they actually won't depend on the basis chosen. Okay, so that's the transpose. And then we're not going to get to it this lecture, but there's something called superoperator, and it's a linear transformation of matrices. And what we can do is we can think of the transpose as a superoperator. So I take X and I sandwich it by Ji and Ji on both sides. Okay. And then, if we then collapse this whole thing here, it's a scalar, right? Xij, that's this right here. Then we can identify this expression with this one. Okay. And these are often called Krauss operators of the superoperator. And we'll be getting to those later. If you not only take the transpose and then take the complex conjugate, that's what we call conjugate transpose. And in physics, we use dagger for that. If you go to math papers, they'll use star. So not only do you take the transpose as we just defined, but then you take the complex conjugate. Okay. And this is actually basis independent, interestingly. Okay. And I believe that's been left as an exercise for proving that one. Okay. So that's something we'll do a lot. Because as an example, evolutions of quantum states are given by unitary matrices. And if you want to think about the reversal of the evolution, then you would do the conjugate transpose. Because for a unitary matrix, the conjugate transpose is the inverse. So it's easy to calculate the inverse for those matrices. Okay. We talked about inner products at the beginning of the lecture. Not only can you do it for vectors, but you can also do it for operators. And how is that defined? Well, we'll use this notation, which is inspired by math notation. I suppose we could have also done Dirac notation for this, but that might be confusing. So it's more common actually in the quantum information literature to use this common notation for Hilbert-Schmidt inner product. Anyway, what you do is this: you take the conjugate transpose, you multiply, and then you take the trace. Okay, and it's well defined for if X and Y are both operators that go from Hilbert space A to Hilbert space B, then it's well defined. So in some sense, they have to be comparable, just like vectors for which we take the inner product have to have the same dimension. This generalizes the usual inner product, right? If the input space is the trivial, like a one-dimensional space, then the operator is actually a vector. Okay. And so if the operators are vectors and you do this operation, then it just reduces to the usual inner product. For more general operators, there's actually a way to encode them in vectors such that this Hilbert-Schmidt inner product reduces to the usual inner product between the vectors. I didn't show that in this lecture. I suppose if we were at the whiteboard, I would do that. So, okay. There's something called the Hilbert-Schmidt norm, and then that's the norm induced by the Hilbert-Schmidt inner product. And it's very similar to how the Euclidean norm is induced by the Euclidean inner product. Something that is pretty neat, and this actually is the encoding of an operator into a vector that I just talked about. So this is something that we'll do a fair amount, this kind of thing. We'll make use of this trick throughout the course. So, and it's kind of like an isomorphism. There's a way to get from an operator to we often call this bipartite vector, two-party vector, because we think of this Hilbert space corresponding to a quantum system that Alice possesses, and this Hilbert space corresponding to a quantum system that Bob possesses. So what this isomorphism allows for is that you can identify every vector with an operator and vice versa. Okay, so how does it work? We're saying that for every bipartite vector, you can write it in this way, where X is some operator and gamma is a special bipartite vector that we call maximally entangled vector. Okay. Here, I'm not making a distinction in the notation of these Hilbert spaces you really should think of them as being different. I suppose we could have put like a prime or a tilde on this one if we wanted to, but we didn't. This maximally, this vector is special, and we often call it maximally entangled vector. And what you do is you take a linear combination of these orthonormal states. You take an orthonormal basis for A, and here the space is the same, so you could take the same orthonormal basis, and then you take this correlated sum, okay? And we'll see later why we call this maximally entangled vector. So how does this work? Let's prove this statement. So we'll let psi, we'll expand it with respect to this orthonormal basis. Remember we said for a tensor product Hilbert space, an orthonormal basis consists of the tensor product of the individual states from the orthonormal bases. So you expand this vector with respect to this basis, and then you get these coefficients that are doubly indexed. If they're doubly indexed, that's a matrix. And we can think of an operator corresponding to this matrix by flipping this ket to a bra, right? And then now we have a linear operator from A to B. So this is the correct choice of the operator that satisfies this condition. And let's just verify that quickly. So why is it true? Well, consider this. Take its definition, take the definition of gamma. And now let's use the property of the tensor product where this identity will act here on this first factor, and then this operator will act on this second factor. Okay, everything's nice and linear, so the sums can come out and the coefficients as well. Identity acted on this, so we just have ket k here, and now we have I overlapping with k on this factor. And we said previously that this is a Kronecker delta, so the sum over k can be eliminated, and then we just get j left over here. But that's precisely how we define psi. So that's the connection, and it's pretty simple. Okay. All right, so let's continue. There's something else that we'll use a lot. It's a mathematical, we'll present it now as a mathematical trick. It does have a physical interpretation. So what is it? If I take an arbitrary linear operator, tensor it with identity, and act on the gamma vector, this maximum entangled vector, then that's the same as doing the transpose of X with respect to the basis. Remember we said that transpose is a basis dependent operation. So if you take the transpose with respect to the basis that defines the maximum entangled vector, then this equality holds. So it's like doing the transpose, doing the matrix over here, performing this operator here, is the same as performing the transpose on the other side and tensor with identity. And in general, these spaces could be different. So this gamma vector will be a maximum entangled vector for the B Hilbert space, and this will be the maximum entangled vector for the A Hilbert space. Remember how this gamma is defined. Oops. It's defined like this. So you run over the sum, and the number of components will be equal to the dimension of the space A. For if we have B here instead, the number of terms in the sum will be dimension of the space B. Okay, so that's one thing to keep in mind. And then the way that we presented it here, the dimensions can be different. And so often this transpose trick is presented only if X is a square operator. such that the input and output spaces are the same. So what is the interpretation of this? I drew this diagram to help give some interpretation. Later on, we'll think of two parties sharing a maximally entangled state. Okay, that's a very special quantum state. It's an entangled state. We'll talk about what that means later on. And here I'm going to think of a top party and a bottom party. So what this transpose trick is saying is that, if the bottom party performs X, it's the same as the top party performing X transpose. Okay. And then later on, we'll be thinking of that the top party and the bottom party can be spatially separated. And so it's kind of remarkable that one person doing one thing is actually the same. Sorry, it's one person doing one thing and the other doing nothing is the same as the first doing nothing and the second doing the transpose of that operation. Okay. So this trick gets used a fair amount in quantum information. Let's now discuss different kinds of operators that come up in quantum information. Hermitian operators are those such that they're equal to their conjugate transpose. These will end up corresponding to what are called observables. And if there's an associated quantum state, an observable along with the quantum state, those generalize the notion of a random variable from probability theory. So what is a random variable? It's a quantity that takes certain values, it takes values with certain probabilities. Like a fair die has 6 different values, 1 through 6, and the probabilities are uniform, 1/6. So the quantum generalization of that is a Hermitian operator paired up with a quantum state. The operator corresponds to the values, like the numbers on the faces of the die, and the quantum state replaces the probability, it generalizes the probability distribution. What are other important operators? Positive semi-definite ones. So these are operators that are not only Hermitian, but satisfy this inequality, such that if you sandwich X by an arbitrary vector psi, then you always get a non-negative number. Okay. If you're familiar with eigenvalues from linear algebra, then there's a well-known theorem that an operator is positive semi-definite if and only if all of the eigenvalues are non-negative. Okay. There's a notation that we will use throughout the course. This is an operator inequality, and whenever you see this, you should replace this in your mind with this statement. X is greater than Z in the operator interval order if I take X minus Z and I get a positive semi-definite matrix. So we could also write X minus Z greater than 0. We use the annotation. Right, you could also write this. And that would mean the same thing. And so what this means literally is like, I compute X minus Z. So to decide whether this inequality is true, I compute X minus Z, I calculate the eigenvalues, and then if all the eigenvalues are non-negative, then this statement is true. A common mistake that's made when people first learn this is they think that this means all of the entries of X are greater than all of the entries of Z, but that's wrong. What it means is exactly what I just said. Okay. And then a subset of the positive semi-definite operators are the positive definite ones. And those are the ones for which the inequality is strict. Okay. It turns out that positive definite operators are invertible, right? So a related condition or an equivalent condition to being positive definite is that all of the eigenvalues are strictly positive. And then if that's the case, then the matrix will be invertible. So we'll make use of positive definite operators a fair amount. The next ones that are very important, and they represent quantum states, are density operators. These are operators that are positive semi-definite such that their trace is equal to 1. Density operators generalize probability distributions. What is the requirement for a probability distribution? All of the numbers in the distribution should be non-negative and they should sum to 1. So density operators are those for which the eigenvalues form a probability distribution. Okay. And then that's kind of the sense in which density operators generalize probability distributions. And this is related to a broader notion that quantum information completely subsumes classical information. So anything that you can do using classical information or classical probability theory, you can embed that into quantum information. And sometimes people will refer to this as quantum probability. It's a term I think more popular with mathematical types. Okay, so yeah, to embed a probability distribution into a quantum state, what you do is you take all the values and just place them on the diagonal of the matrix in the standard basis. And then you get a legitimate quantum state. And then, that's how you embed all of probability theory into quantum probability or quantum information, so to speak. But then quantum information allows for richer possibilities because the off-diagonal elements can be non-zero. And then when that happens, it's said that those off-diagonal elements correspond to what are called coherences. Okay, another class of operators that are important are unitary operators. So this is how they're defined, and we talked about them earlier. They're ones for which their inverse is given by the conjugate transpose. Okay, and these are important because they correspond to evolution of a closed system, right? So, if you've taken quantum mechanics before, you learn about the Schrodinger equation. It corresponds to evolution of a closed quantum system. And then if you solve the Schrodinger equation, you find that there is a unitary operator that tells you how your state vector will evolve. Okay, so these are quite important in the context of quantum mechanics and quantum information. Generalizing a unitary operator is what we call isometry. A unitary operator has to be square. It maps from a Hilbert space to the same Hilbert space. An isometry you can think of as a rectangular matrix. So it goes from one Hilbert space to another, and typically the output Hilbert space is larger. And it's just that you need the V dagger. V is the identity. If you calculate V dagger, it need not be the identity, but it ends up just being a projection onto the output Hilbert space. you can prove that it's a projection by using the definition we're about to give and this property. If I was saying that VV dagger is a projection, but the way an isometry is defined is that V dagger V is the identity. So isometries will come up a fair amount because typically what we'll do to evolve a state is that we'll take the state vector, we'll tensor in a standard vector, like the zero vector. What I mean by zero is the vector labeled by zero, not the all zeros vector. So we'll tensor it in, and then we'll perform a unitary operation on the joint Hilbert space. And then what you can show is that the overall action of tensoring in the standard vector and doing a unitary is equivalent to performing an isometry. That might be left as an exercise. Since we have a fair amount of time, maybe I will attempt to show you this with annotation. So how does this work? We take psi, we tensor in 0, okay, and then we do a unitary. Okay, so why is the action of tensoring in 0 and then doing a unitary an isometry? Well, let's calculate what we get by doing the dual of everything. So we do U dagger and then psi tensor 0. Okay, this right here is the identity matrix, so that's gone. And then we're left with the tensor product of psi with itself and 0 with itself. Okay, so that will evaluate to this. They're using definition of tensor product. But this is 1, right? So it's gone. And so what we're seeing here is that, and then this statement is true, this equality is true for all vectors psi, right? So since that's true for all psi, the action on psi okay, so that means the overall action of U and then, sorry, tensoring with 0 and then doing the unitary leads to the identity matrix acting on this reduced Hilbert space. And so, we can think of, we can define the isometry V in this way, right? Take V psi to be equal to U psi tensor 0. Okay, so these steps show that when you define V in this way, V dagger V is the identity matrix. Okay, is that clear? Any questions on that? That might be kind of new for some people. All right, we'll go ahead and clear that. Okay, let's continue. Projections, what is their relevance? Well, let's define them first. So they're linear operators, they're square operators that have the same input and output Hilbert spaces. Not only are they Hermitian, but they're such that when you square them, you get the same thing back. Okay, so that's the defining property of a projection. You can think of projection as like the shadow that a vector casts on some surface, right? So if you apply the projection and then apply it again, it doesn't change anymore because it's already been projected down to a space. Why are these important? Well, eventually we'll talk about measurements of quantum states, and the most basic kind of quantum measurement is described by a set of projection operators. So that's the main context in which they come up in quantum information. Previously, we talked about data compression, okay? And today we talked about how we can embed classical into quantum. So I want to make contact with the Shannon data compression theorem, right? We said that an information source is described by a probability distribution, and we drew a histogram, right? And then data compression corresponded to keeping only the high probability letters in the alphabet that describes the information source. That is, if we were to embed that probability distribution into a quantum state, cutting out certain values corresponds to a projection, okay? And so you can think of our data compression scheme as kind of like a measurement. Like we're asking, are you in the high probability set or not? That's a binary question. And that can correspond to a quantum measurement described by a projection operator, like asking, are you in this space or a different space? So that's a way that projections connect to information theory. And then, yeah, indeed, when we talk about decoding classical information, we'll have to construct measurements and we'll use projections there. Okay. I mentioned earlier the singular value decomposition as the fundamental theorem of linear algebra. So let's review that now and write it in Dirac notation. Okay, so for every linear operator X with rank R, remember we defined rank as the dimension of the image, but I actually think it's easier to think of rank as the number of singular values from this theorem, okay? So for every operator X, there exists a set of singular values. This is a set of real numbers that are strictly positive, and there are corresponding orthonormal sets. So there's an orthonormal set for the output space, there's an orthonormal set for the input space. The number that you need is no larger than the rank, okay? And then you can write the operator in this way. Take the duals of the vectors from this set, and then that acts on the input, and then take these vectors and pair them up in this way, and then sum them. And then the scaling corresponds to the singular value. So what this allows you to do is to think of an operator in kind of a way like you have these orthonormal sets, right? So I can think of the action of this operator as if I have an incoming vector psi, for all possible k, I'll act with fk on psi, and then I'll get some number. And that gets taken to be a coefficient of this ek vector. and then it gets scaled as well. Okay. And then you do that for all possible vectors in the set, for all possible indices k in the set, right? So it's like, if I were to input fk prime, then since these are orthonormal, the only one in the set that would be chosen is when k equals k prime. That's all that would be left. And that fk prime would go to ek scaled by this singular value, right? So that's another way to think of it. And yeah. If these singular vectors are all ones, then does anybody know what kind of operator that would be? We talked about all these different kinds, 1 through 7. So maybe to get some participation from y'all, I'll ask that question. Suppose that the SKs are all equal to 1. What kind of operator is that?
Would that be unitary?
Very close. It's going to be an isometry in general, right?
Okay. Yeah.
You see it? Because like you could check that if I compute, suppose SKs are 1, I do x dagger x, you'll get that that's equal to the question maybe should have been phrased a little more carefully. Suppose that the rank R is the same as the dimension of the input Hilbert space. Then indeed it's an isometry, right? But if that's not the case, I think you'd call it partial isometry. Anyway, so suppose that the rank is equal to the dimension of the input Hilbert space. Then you could do a calculation to verify that x dagger x will be the identity on the input Hilbert space. Okay. If the dimension of B is the same as the dimension of A, then Tristan, indeed you're correct. It would be a unitary matrix. Yeah. Good. Okay. There's something called Schmidt decomposition, which is interestingly enough directly related to the singular value decomposition. And yet this tells us something fundamental about entanglement. And that's something we'll get to later. Okay. So if I have a bipartite vector, you can write it like this. And notice the similarity to the Schmidt decomposition, right? It's kind of like all we did was we actually have to flip E and F. Sorry about that. So we have to flip E and F, and then we flip this bra to a ket, and then we get this right here. And these SKs are positive, strictly positive anyway, so we can take their square root, and we get these lambda k's. Okay, so yeah, it's possible to do this for any bipartite vector. And the way that you see that this is possible is precisely through this trick that we talked about previously, that you can identify a bipartite vector with a linear operator acting on the maximum entangled vector. Okay, so the way that we'll prove the Schmidt decomposition is we'll use the singular value decomposition of this, and then we'll just like go back and forth. Okay. But let me finish stating what the Schmidt decomposition is. It's very similar to the singular value decomposition. So these are strictly positive numbers. R is called the Schmidt rank of this vector. It's going to be the same as the actual rank of that operator corresponding to psi. These are called Schmidt coefficients, and then these are orthonormal bases. The connection to entanglement theory that we'll get to later is that a bipartite state vector is entangled if and only if the Schmidt rank is greater than or equal to 2. If the Schmidt rank is 1, then there's just a product of 2 vectors alone here, right? And then it's what's called, if it's a state, it's what's called product state. Okay, how do we prove this? We can expand psi with respect to an orthonormal basis for the tensor product Hilbert space. We get these coefficients. And then following the proof that we had previously to identify psi with x, we just define this operator x, okay? To define it, we just flip this ket to a bra, okay? And that gives an isomorphism between psi and x. It's the same as the isomorphism that we talked about previously. Then what we do is we just say, oh, okay, well, this is the operator x. It has a singular value decomposition. We can alternatively represent it like this, where these are strictly positive coefficients, and these are these singular vectors. Then we flip the bra back to a ket. When we do so, we'll actually get a complex conjugate, okay? And then we'll define EK to be these vectors right here. And that's the Schmidt decomposition, okay? And that gives you some sense of the proof. Any questions about that? All right. Okay. I think there's really just 2 more things that I want to talk about, and we have 10 minutes left anyway. And if there are like questions for discussion, then we can take the remaining time for that. See what's left. Polar decomposition and spectral theorem, and that. Okay, so polar decomposition, an arbitrary square operator, we can write it as a unitary times a positive semi-definite operator. And I should have written this in the notes. Let me write it now. It's called polar decomposition because it's analogous to the polar form of a complex number, right? So a complex number, you can write in polar form like this. This is the magnitude, this is the phase. The magnitude is non-negative, and this complex phase is on the unit circle. So the polar decomposition generalizes this polar form, right? The positive semi-definite operator generalizes the magnitude, and sorry, there's someone working on the yard outside. Can y'all still hear me? Yeah. Do you hear the noise? No. All right. So Zoom has good filtering capabilities. Just distracts me. Okay. So why this is actually a direct generalization of the polar form, right? A positive semi-definite operator, we said it has non-negative eigenvalues. So each of those eigenvalues you can think of as being like magnitudes on their own, right? A unitary matrix, it has eigenvalues that lie on the unit circle, and all of its eigenvalues can be written as, like this, as complex phases. And so if your linear operator is trivial, like a one-dimensional operator, it's a complex number, and the polar decomposition reduces to the polar form. But then beyond that, you have this. How do you prove it? You use the singular value decomposition. So there's a simple way to do that. So let me there's a point I wanted to make for the singular value decomposition, to have some notation that corresponds to what you learn in a linear algebra class. You can also write the singular value decomposition like this. U, I guess sometimes we write dagger, and then V. So sigma would be generally a rectangular matrix where the diagonal elements are the singular values. Okay. U will be a unitary matrix. So U dagger, you could write like this. It'll take this orthonormal basis to the standard basis. Okay. And then this sigma matrix is diagonal in the standard basis. And then V will be a unitary matrix that takes the standard basis to this EK basis. Okay. So that's a way to think of this in terms of the usual, like this is how you'd usually see the singular value decomposition in a linear algebra course. And so that's how this form connects with this one. All right. Okay. Spectral theorem. This is something we'll use a lot, and it corresponds to eigen decompositions. So it holds for every operator that's normal. What does that mean? The operator commutes with its conjugate transpose. So that includes unitaries. It includes Hermitian operators. It includes at least those. Okay, so for every normal operator, there's an integer n such that you can write x in terms of these eigenvalues. Let me say that the way that I'm writing this is a unique decomposition. Okay, so these lambda j's are distinct eigenvalues, and these pi j's are eigenprojections, also called spectral projections. And they project onto eigenspaces with eigenvalue lambda j. Okay. These spectral projections satisfy the completeness relation, such that if you sum them, you get the identity, and they are orthogonal to each other. Okay. So how does this get used? In the context of quantum mechanics, a Hermitian X is what we call observable. Hermitian operators will have real eigenvalues. So the eigenvalues will correspond to the values that you measure, and the measurement will be described by these projections. Okay. There's another way that the spectral theorem is presented in the book. After it's presented this way, a non-unique way to have the spectral decomposition is like this. Let me use a different index, k. I'll write mu k, just so it's totally separate. And psi k. Oops, sorry. Psi k. So these would be the eigenvectors, and these are the eigenvalues. This is not a unique decomposition, right? An example is given by the identity, right? The identity will have eigenvalues all equal to 1, and then these eigenvectors could be chosen from any orthonormal basis, right? And then, using this decomposition, you can see that X acting on psi k gives mu k psi k. The other thing I forgot to say is that these eigenvectors will be orthonormal, and then that's how you see that this relation is true, and it's actually identical to this decomposition. Okay, so we'll make use of this form as well as this form. But keep in mind that this one's unique because these degeneracies where you could have eigenvectors with the same eigenvalue are captured by these spectral projections. Okay. Final thing we'll say is the positive part and negative part of a Hermitian operator. So this is a unique decomposition of a matrix, and it's quite useful. We'll use it a number of times. We can write X as a difference of a positive. We can write as a difference of two positive semi-definite operators. One is called the positive part, and one is called the negative part. Keep in mind that the negative part is a positive semi-definite operator. Okay, the terminology can be a little confusing. The critical thing is that the positive part times the negative part is equal to 0. So these two matrices are orthogonal to each other. How do you get it? You take the eigen decomposition from here, include all of the terms such that the eigenvalues are non-negative, and you get the positive part. Okay. Here, the negative part, you include all of the eigenvalues that are negative, strictly negative, but then you take their absolute values. And that's why the resulting operator is positive semi-definite, and then you put the minus sign in front. So it's the convention to write it like this, the difference of the positive part and the negative part. This kind of thing comes up a lot. Like, we're interested in computing what's called trace distance of two quantum states, and then to evaluate it, you often use this kind of thing. All right, that's all I have for today. Thanks for tuning in, and we'll be in person, I guess, on Wednesday. Any questions for me? Okay. So yeah, in the meantime, you should start going through chapter 2. Start trying the homework exercises that you've been assigned in chapter 2. I delayed it by a week, but still, I think, if you have the time, it'd be good to start going through this, because we're just gonna, probably the next 2 or 3 lectures, we're gonna try to make it through chapter 2. Okay, so what remains is to talk about norms and semi-definite programming and notions like convexity, various notions of limits, supremum, infimum, that kind of stuff. Okay. All right, so y'all have a good Labor Day weekend, and I'll see you on Wednesday.